This third lecture on Fourier series, we shall first recapitulate what we have done in the last two lectures. In the first lecture, we have discussed the completeness and orthogonality of sine and cosine functions, sines and cosine functions in an interval of 2 pi. And secondly, in the second class, we have stated Dirichlet's condition, which states that if a function f of x is said to satisfy Dirichlet condition in AB if the function is single valued. Then secondly, it is either continuous. F of x is either continuous or may have finite number of finite discontinuities, or may have finite number of finite the function may have finite number of maxima and minima. F of x may have finite number of maxima or minima. Fourthly, integration from a to b modulus of fx dx exists. Exist means all finite. An additional condition, f of x is periodic. This condition is extraneous, as we have already said. A function which satisfies these conditions are called piecewise regular function. I request the audience to see the picture or a picture of piecewise regular function as given in Emily Boas. The picture of a continuous piecewise regular function as given in Boas is very instructive. This Dirichlet condition, if we have a function which satisfies Dirichlet condition, then it can be expanded in Fourier series, trigonometric Fourier series, with a0 plus n is equal to 1 to infinity an cos of 2n pi x delta plus bn sine of 2n pi x upon delta, and the expansion coefficients an and an's and bn's are given by Euler formula. Furthermore, if we estimate a function by this, then if the point of expansion, that is x, is a continuous function, then Sn, the partial sum Sn, approaches the functional value if the point of expansion is a continuous point, and it reaches, and Sn approaches to the average value when the point of expansion is the point of finite discontinuity. The thing that I want to add over here, that Dirichlet condition is the sufficient condition. It is sufficient. It is not the necessary condition. The minimum condition, what is not at all known. That is, what should be the minimum criteria that a function should satisfy so as to so that it can be expanded in Fourier series is not known clearly. But one may say that if a function satisfies Dirichlet's condition, it can be expanded in Fourier series. Now, with this recapitulation, I will consider an example, and then we will again come to the theory. As an example, we choose what is called square waves. That is the function. Example 1. The function is defined as this. This is equal to minus h for x less than 0 greater than minus c, and it is plus h, it is h for x less than c and greater than 0. And furthermore, it is provided the function is periodic. F of x is equal to f of x plus 2c, as 2c is the periodic. So first thing is that we must draw the graph of the function. So this is f of x axis and this is x axis. 0, c, 2c, 3c, etc. This is minus c, minus 2c, minus 3c. Between minus c to c it is h, and between 0 to c it is plus h. This is minus h and this is plus h. And for other, since the function is periodic, we can expand it. So this is the periodic extension of the function. So this is the function. We see that at nc, or at x is equal to nc, where n is an integer, the function has a discontinuity. These are the points of discontinuity. And the amount of discontinuity is equal to 2h finite, which is finite. So we can expand the function in Fourier series. So and what we expect upon expansion, that if we choose x is equal to 0, the function must give the average value of the function, which is plus h, and average of h and minus h, that is 0. And if we expand the function over here in this part, this should give you the value of h, and over here it should give you the value of minus h. So first of all, we see that in this case a is equal to minus c, b is equal to plus c. So delta is equal to b minus a is equal to 2c, and the argument was 2n pi x by delta, which now becomes 2n pi x by 2c. So this is n pi x upon c. This is the argument. So we expand the function in Fourier series as a0 upon 2 plus summation over n is equal to 1 to infinity an cos of n pi x by c, n pi x upon c plus bn sine of n pi xc. Now the expansion coefficients. Coming to the expansion coefficients, a0 was defined by 2 upon delta a to b fx dx. This is the general definition. This in particular case becomes 1 by c because delta is equal to 2c. This is minus c to plus c f of x dx. This is 1 upon c. We write from minus c to 0 dx, and in this range the function is minus h, plus 0 to c dx, this is plus h. So this result is 0. Now coming to an. Similarly, an is 2 by delta a to b f of x cos of n pi xc dx, which in this case becomes 1 upon c. From minus c to 0, the function value is minus h times cos of n pi x c dx, and for the other half, this function is positive, so this is 0 to c cos of n pi x c dx. So this can be written as, we can take c out, h out, so this is c by h, and when we integrate we will get c by n pi, so this is taken out. This will be sine function, so sine of n pi x c within limit minus c to 0, and this is sine of n pi x c 0 to c. So if we write, this part becomes this is h by c. So cc cancels out. This is h by n pi, and then we will have the upper limit is 0, so it is 0, and the lower limit is, there are 3 minus sign, one from here, other one from minus, the minus from lower limit, and one from this sine of minus c. So this is altogether minus sine of n pi, because at c it is n pi, and from here we will have, this is from the first part, this is the contribution of this part, and for the second part you will have sine of n pi minus 0, so the altogether result is 0. One point I like to mention, that same conclusion can be arrived at more easily by using proper argument that we will discuss in the second half of this lecture. For the time being, I am calculating the coefficients by brute force, that is without going to any reason or period, evenness or oddness. I am going to calculate it directly and land up with the result that a0 is 0 and an is 0. So the even coefficients are 0. Now I am going to calculate b, that is the coefficients connected with the sine part. So bn as usual, 2 by delta a to b f of x sine of n pi x c dx, which in this particular case becomes 1 upon c from here, and then minus h minus c to 0 sine of n pi x c dx plus h 0 to c sine of n pi x c dx. Again, as in the earlier case, taking h out, and if when we integrate we will get at a factor c by n pi with a minus sign, so I put a minus sign over here. This minus sign is from the integration of sine function, so this is minus cos of n pi x c within limit minus c to 0, and from that we'll have cos of n pi x c within limit 0 to c. This part is minus h by n pi, and this part minus cos of 0 is 1 minus cos of n pi minus cos of n pi, cos being an even function, cos of minus n pi is cos of n pi. Plus here we have cos of n pi minus 1 . So these two just adds up, and the result can be written as h upon n pi 1 minus cos of n pi multiplied by 2, one from this, one from this. So result is 2h upon n pi 1 minus minus 1 to the power n, because cos of n pi is equal to minus 1 to the power n. So the result is, final result is, this is when n is even, this is 0, so 0 for n is equal to even, and for all values of n we will have 4h upon n pi. We will have 4h upon n pi for n is equal to odd integers. So this is the conclusion. So we write the conclusion over here, that after evaluation we come to the conclusion that a0 an are 0, a0 is equal to 0 is equal to an's one part, and for bn we will have 0 for n is equal to even, and 4h upon n pi for n is equal to odd. This is the evaluation of the constants. Now if we try to expand this function, this now becomes, since this is 0, this simply becomes summation over n is equal to 1 to infinity bn sine of n pi x upon c, and n is 1, 3, 5, so on so forth, n is odds. So we can write it as n is equal to 1 to infinity. We pick up the restriction or remove the restriction, and we write it as 4h upon 2n minus 1 pi. So when n is equal to 1, it is 1. When n is equal to 2, it is 3. Sine of 2n minus 1 pi x upon c. This is the Fourier expansion. Writing explicitly this becomes, we can take 4h by pi out because it is not n-dependent, and for n is equal to 1, the result is 1 upon sine of x pi by c. For n is equal to 3, we will have 1 upon 3 sine of 3 pi x upon c plus 1 upon 5 sine of 5 pi x by c, and so on and so forth. Now if we write Sn, the sum of first n terms, so Sn would be there will be n such terms. So this is the partial sum. If we plot the partial sum, we will find that as n increases, the actual function becomes like this. That is to say that the function with increasing n, this amount of oscillation will decrease. This amount of oscillation will decrease, that as we increase n, this oscillation, the amplitude of the oscillation will become smaller and smaller, so that the function the expansion approximates the function in a better and better way. On the other hand, there will be another thing. There will be an overestimation of the function near the points of discontinuity. As you increase the value of capital N, it is found that this region where overestimation takes place, this region, the width of this region decreases with increasing n, but the amplitude of this overestimation increases with n. So if we calculate with capital N is equal to 10, say the width is over this region. If we use capital N is equal to 20, the width will decrease. But this height or kink, will increase with increasing value of capital N. This is a general feature of Fourier expansion. If we expand the Fourier series of a function which has a point of discontinuity, then at the point of discontinuity, the function the Fourier expansion overestimates the function, and the kink that appears increases with increasing n. That is to say that this kink cannot be subsidized or remedied by increasing n. As you go on increasing n, this kink will go on increasing, but the extent will remain same. So it, in other words, it reaches a delta function type of. This is a very important phenomena known as Gibbs phenomena. This is Gibbs phenomena. So in other words, Gibbs phenomena is that whenever we expand a Fourier function in Fourier series having a point of discontinuity, then at the point of discontinuity the Fourier expansion overestimates the function and kink appears. The amount of kink increases with increasing number of partial sums. This is Gibbs phenomena. We will see for every function having point of discontinuity, Gibbs function increases. In the study material that I have provided you, this graph has been plotted for different values of capital N. Otherwise, you can consult any standard books on mathematical physics. One important thing I want to extract out of this, that is, if we put x is equal to 0, x is equal to 0 is the point of discontinuity. So the average value at x is equal to 0 of the function is 0. If we put x is equal to 0, the sine functions are 0. So the estimated value of the function is 0, as we have told in the theory. Now, what happens if we put x value in between this? If we put a value of x in between this, then as appears from the graph, the Fourier expansion approaches more and more towards the functional value. Now we shall use this technique to find important relation. So what we do is this. At x is equal to c by 2, f of x we know it is h. So we expand this as there. It is h on the left hand side. On the right hand side we will have 4h by pi within bracket. This is sine of x is equal to c by 2, so this is pi by 2, plus 1 by 3 sine of 3 pi by 2 plus 1 by 5 sine of 5 pi by 2 plus 1, so forth. This goes to infinity. So this is 4h by pi, and then it is sine of 1, and this is minus 1, this is plus 1, or h cancels out. We can write 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 is equal to pi by 4. This is another utility of Fourier series, that some particular series, infinite series, can be estimated by using Fourier series. So this is the first example that we have considered. Now we will come back to theory to see that these things that we have done, we have calculated a0, an and bn for this function, but from the figure it appears the function is an odd function. So now we shall see that we need not to go for the calculation of these, because they would be zero trivially. We need to calculate only b, and even for the b the calculation may be simplified to a good extent. So our topic is the Fourier series for even and odd functions. We have a function, consider a function which satisfies Dirichlet's condition within the interval AB. So we write it as a0 by 2 plus summation over n is equal to 1 to infinity an cos 2n pi x by delta plus bn sine 2n pi x by delta for function of with negative argument. This is not dependent on this. Cosine function being an even function, we write it again. Sine function being an odd function, and negative sign will come. Here we have used cos of minus x is equal to cos of x, and here sine of minus x is equal to minus sine x, the property that we have used. It is known to us from school standard. Now what we'll have? If we have a function which is an even function, so for even function is defined as we have f of minus x is equal to f of x. This is the sine even function. So if we write this from left hand side, we can write it is a0 by 2 plus summation over n is equal to 1 to infinity an cos of 2n pi x by delta minus bn sine of 2n pi x by delta. This is for left hand side, this is for this part, and for the other part we write a0 by 2 summation over n is equal to 1 to infinity n this term cancels with this, and for each value of n this part cancels with this. So we will left with apart from the factor 2 this immediately leads us to conclude that Pn is equal to 0 for all n when f of x is even. So a even function will have only the even parts. So this is the even part because this does not change by changing x by minus x, and this is also the even part. This is the odd part which must be dropped from the expansion, as this is the same thing that we have argued at the beginning, that an even function can be represented in terms of cos functions. Similarly, for an odd function, we will have For an odd function we will have this is equal to minus, so and there will be an overall minus sign. So we see that the result is a 0 by 2, which will survive because this is minus. When taken to this side it will be plus. This is 0. That is possible for all function only when a0 is equal to 0 and an is equal to 0 for all n's. Natural number for f of x odd. So we see that an odd function will have only the odd components. Now come to the expansion of this Fourier series. So for a function having, if it is be either odd or even, then the expansion simplifies. A function which is either even or odd is said to have a definite parity. A function which is odd function, when it is expanded in power series, will have only the odd powers of x. On the other hand, a function which is even, when expanded in power series, will have only even coefficients. So we write f of x which is even function, even, it will have a 0 by 2 plus summation over an cos of 2n by x by delta, and f of x which is an odd one as we shall see that the expression for an and bn will be slightly different for even and odd functions. So I would like to use a superscript this to denote this for even and odd function, although for odd function a's will not appear, and for even function b will not appear. If we have a function with definite parity, then one defines it in a symmetric interval. For a function having definite parity, means either even or odd, one is defined as symmetric interval, is intervals. Let minus c to plus c, in which case delta a is equal to minus c, b is equal to plus c, delta is equal to b minus a is equal to 2c. So what we'll have, we will have the a0 for even function is originally defined to be 2 by delta from a to b f of x dx, which in this case becomes 2 by 2c and from minus c to plus c f of x dx. This becomes 1 upon c. This is 1 upon c, and since the function is even function, we can split up into two intervals from minus c to 0 and from 0 to c. In each case the function will remain the same, and you note the change in the limits of integration. In the example, we evaluated the limit from minus c to plus c and landed up with this result. So note that there is a change. For firstly, this limit is considered, the integration has to be considered only over one part, and there will be appearance of two factors in the factor are related with it. So this is the an, and this is considered ane. Similarly, it is 2 by delta a to b f of x cos of 2n pi x. So sorry, 2 will not be there because this is n pi x by c dx. Now first thing is that this is 1 by c, and then the integration is minus c to plus c f of x cos of n pi x c dx. Since this is even, so the product function is an even function, which we can write as 2 by c 0 to c. Note the change in interval. So this completes the Euler formula for an even function. So for even function we write a0 e is equal to 2 upon c, and a n, again it is 2 upon c 0 to c f of x cos of n pi x c dx. And for an odd function, we are to find out bn. For an odd function, bn odd, actually it is 2 by delta a to b f of x sine of n pi x 2n pi x by delta dx, which simplifies to 1 upon c. From here, limit minus c to plus c f of x sine of n pi x c dx. The function is odd. This is also odd, so product of two odd function is an even function. So if we exploit this property, we get this is 2 by c 0 to c f of x sine of n pi x c dx. This is the simplification that we have. So we have bn for odd function the function itself is defined in the interval from plus c to minus c to plus c. Now coming to the example we have considered. The example we have considered earlier is an odd function. So looking at the graph of the function together with its periodic extension, it was apparent that the function was an odd function. So we need not to calculate a's for the function. We just write that the function being an odd function, all the a's would be 0 trivially, and one need only to calculate b. And if we calculate b using this expansion, we do not need to calculate the two terms that we have done in the actual calculation. B can be calculated using half the level. So this is the simplification of Fourier series for even and odd function. Now I am going to prescribe the points or the algorithm to be followed in evaluating a Fourier series. First thing, steps to be followed in solving problems. First, plot the function, together with its periodic extension. Fix the argument. That is 2n pi x by delta. Fixed. Thirdly, if f of x is equal to even, calculate only a0 and an's. If f of x is odd, calculate only bn's. If f of x does not have any definite parity, that is, the function is neither even or parity, calculate all a0, an's and bn's. There will be a check check the independence of the coefficients. This way will be discussed in the next class. Will be next to be discussed in future. In the next class, we shall consider few more examples on Fourier series, and then from that we will come to this discussion.